All right, the next few videos we're going to be watching are going to be going over Chapter 4, which is titled An Introduction to Differential Equations. We don't get too much into differential equations in Math 220, but many of you will take another class that's actually just called Ordinary Differential Equations, and you study a lot about different methods for solving differential equations and also applications of those types of equations. So if we jump into section 4.1, that's what this video is going to cover. It basically just, as the title says, goes over the basics of differential equations. We're going to be talking about definitions. We're going to talk about solutions of differential equations and being able to identify whether or not an equation is a solution. And so let's go ahead and jump in by starting to look at a couple definitions. The first one is actually the definition of a differential equation. It says a differential equation is an equation involving an unknown function y and one or more of its derivatives. So that's what kind of sets it apart. Differential equations, as opposed to equations you've seen before, not only have y in it, but they also have the derivative. So it could be a y prime or a y double prime or even a third derivative. As long as there's one or more of its derivatives, then it's considered a differential equation. And it says the solution to a differential equation is a function y equals f of x that satisfies that differential equation. That means makes it true when when that function and its derivatives are substituted into the equation. So let's take a look at one more definition, and then we're going to look at an example to kind of see what we mean by these definitions. The other definition is the order of a differential equation. So the order is the highest order of any derivative of the unknown function that appears in this equation. So if the highest derivative is a first derivative, then it's order 1. If it's a second derivative, then the order is 2. So example 1 has some examples of differential equations. Notice all 4 of these equations have at least the function and its derivative. So in the first one, you can see y, there's the function, and then you can see its first derivative. So stating the order, the highest order of the derivative, or the highest derivative, first derivative, second derivative, third derivative, and so on. The highest one is first derivative. So the order on this first one is first order. This is a first order differential equation. And instead of writing differential equation, I'm just going to write DE for short, differential equation. All right, if you move on to the next one, you'll see a second derivative minus 6 times the first derivative plus 8 times the function equals 0. So here we have a second derivative. So this is a second order differential equation. All right. And the next one, we have y prime minus y equals e to the 2x. So the highest order derivative is first derivative. So this is again a first order differential equation. And so what do you think about the last one? What do you think? We have dy dt to the third, or the third derivative, minus t times dy dt, minus t squared minus 1 times y equals e to the t. Notice there's no second derivative, but there is a third derivative, so this is going to be a third order differential equation. Third order dE. Okay, so now you've gotten a little taste of what differential equations might look like. And again, I said this verbally, but let's go ahead and specify this notation. It's not one we see all the time, but that means the third derivative. So you've seen some ideas, some examples of differential equations, and you know how to classify them by their order. Let's go ahead and look at another equation, or another example, excuse me. Example 2 talks about being able to verify if a solution is actually a solution, or if an equation is a solution to a differential equation. So it gives us a differential equation, y prime minus y equals e to the 2x, and it says, is y equals e to the 2x a solution? Well, so let's go ahead and look at this. So if we have y equals e to the 2x, we know that in order for it to be a solution, we have to be able to plug it and its derivatives into the equation, the differential equation, and the equation must be true. Notice the equation not only has y, but also has y prime, so we're going to need to go ahead and find y prime. And in order to find y prime, we have to use the chain rule, because we have the derivative of e to the 2x is e to the 2x times the derivative of the inside. The derivative of 2x is 2. I'm going to rewrite this with the constant in the front. And so this is our derivative here, and we have our function. And so in order to check to see if it's a solution, we just go ahead and plug into our dE. So we have y prime minus y equals e to the 2x. And let's go ahead and substitute. So we can substitute that in for y, then we can substitute the derivative in for y prime, and we'll see what we get here. So plugging in, we have 2 e to the 2x minus e to the 2x equals e to the 2x. And yes, if we simplify the left-hand side, 2e to the 2x minus e to the 2x is e to the 2x. And we can, of course, see that the left-hand side is equal to the right-hand side. So do we have a solution? Yes, we do. Okay, so let's just go ahead and state that. We can say yes, y equals e to the 2x is a solution. Okay, so I want you to go ahead and try this on your own for the second question. It says, how about y equals e to the x plus e to the 2x? So go ahead and pause the video and try to verify that on your own, and then we'll come back and discuss it. Okay, I'm glad you had a chance to look at that on your own. Hopefully you're able to do that with no problem. I'm going to go ahead and go over it with you now. So if we have y equals e to the x plus e to the 2x, then we can see that y prime is going to be e to the x plus 2e to the 2x. And taking our equation y prime minus y equals e to the 2x, we can go ahead and substitute in there. And when we do that, we get e to the x plus 2e to the 2x minus y, and y is e to the x plus e to the 2x. And that's going to be equal to e to the 2x on the right-hand side. And then we want to go ahead and distribute our negative sign in here. So both of these terms are actually going to turn negative. Let me go ahead and rewrite that. I have e to the x plus 2 e to the 2x minus e to the x minus e to the 2x equals e to the 2x. And first of all, the e to the x's are going to subtract away. And then we're just left with 2e to the 2x minus e to the 2x, which, like we saw in the first example, first part of this example, that simplifies the e to the 2x. So we do end up with a true statement. So once again, we can say yes, y equals e to the x plus e to the 2x is a solution. So that's kind of an interesting result, because we had a differential equation, y prime minus y equals e to the 2x, and we now have these two different equations that are solutions to the same differential equation, which is not something that's uncommon in differential equations. So let's go ahead and talk now about the difference between a general and a particular solution. I'm going to go ahead and read through this paragraph. It says it can be shown, just like in the example we did above, example 2, in the same way it can be shown that both y equals x squared and y equals x squared plus 4 are solutions to the differential equation y prime equals 2x. The only difference between these two solutions is a constant, right? The second one had that plus 4 added to it. If the last term was a different constant, the question is, would it still be a solution to that differential equation? Well, it turns out that in this example that any function of the form y equals x squared plus c, where c is a constant, is also a solution. So here's where we get into our definition here. The solution, y equals x squared plus c, is an example of a general solution or a family of solutions. So any of those family of solutions with a plus c as a constant, we call that a general solution. But one of those in particular, so if we took, for example, y equals x squared plus 4, a specific one of those versions of the general solution, y equals x squared plus 4, we call that a particular solution. And let's go ahead and see how we can actually find a particular solution. And example 3 is an example of that. So if we take a look at example 3, it says find the particular solution to the differential equation y prime equals 2x passing through the point 2, 7. Now we saw in our little discussion above that the general solution to y prime equals 2x is y squared, or it's not y squared, y equals x squared plus c, right? That is a general solution to y prime equals 2x. So how can we figure out what the particular solution is that passes through the point 2, 7? Well, we're going to use our general equation, our general solution, y equals x squared plus c, and we're going to plug that point in. So we're going to take y equals x squared plus c, and we are going to substitute in, let's make a little note here, we're going to substitute that point, 2, 7. So, of course, we know if we have a point, 2 comma 7, x equals 2 and y equals 7. So when we do that, we get 7 is equal to 2 squared plus c. Well, 2 squared is 4. If we subtract that over, that easily tells us that c is equal to 3, right? So now we know the constant of our general solution that is good for the equation that passes, it's good for the solution that passes through the point 2, 7. So what we can say is the particular solution in this example, solution is y equals x squared plus the constant we just found, 3. That is our particular solution. Okay? So I'm going to let you go ahead and do one of these on your own. Example 4 says, find the particular solution to the differential equation y prime equals 4x plus 3, passing through the point 1, 7, given that y equals 2x squared plus 3x plus c is a general solution to the differential equation. So go ahead and pause the video and try this one on your own, please. All right, so let's go ahead and check what you got. I'm going to go ahead and write out that general solution, y equals 2x squared plus 3x plus c. And again, just like in the last one, you should plug in that point. It's going to be the particular solution that passes through the point 1, 7. And when we plug in that point, what do we get? We get 7 equals 2 times 1 squared plus 3 times 1 plus c, which basically gives you 7 equals 5 plus c, where c is equal to 2. So that tells us what our particular solution is. Our particular solution should be y equals 2x squared plus 3x, and our c we found was 2. All right, so now you know the difference between particular solutions and general solutions, and you know how to find a particular solution. Let's get into example 5, which talks about how to verify that we have a solution to any initial value problem. So it says verify that y equals 1/4 minus x squared to the negative 1/2 power is a solution to the initial value problem y prime equals xy to the third, where you have y of 0. So when x is 0, y is 2. So the first thing we're going to need to do, what do you think? What should we do first? If we have a problem like this, how are we going to verify? Well, we already know that to verify solution, we're going to plug the function in and its derivatives in. There's just one difference here. This is an initial value problem, so we got to see how that factors into it. So just like the example we did earlier, we also need to find the derivative. So if we have y equals 1/4 minus x squared to the negative 1/2 power, we need to find the derivative there. So y prime, we got to use the chain rule here, so that power has to come to the front, negative 1/2. Keep the stuff on the inside. Then we subtract 1 from the power, which is going to make this minus 3/2 power. And then we need to multiply by the derivative of what we have inside. The derivative of 1/4 is 0, minus the derivative of x squared is negative 2x. And so let's go ahead and simplify. Of course, we have negative 1/2 times negative 2x. That negative 1/2 is going to cancel with the negative 2, just leaving x. And so we can go ahead and rewrite this. We can rewrite this as x over 1/4 minus x squared to the positive 3/2, because we had a negative 3/2 power. All right, so we're almost at the point where we can go ahead and plug in. We do want to verify our initial value, so we'll verify the initial condition. The initial condition says that y of 0 is equal to 2, and we know that y is equal to 1/4 minus x squared to the negative 1/2 power. So y of 0, we're going to plug in 0 for x, so it's going to give us 1/4 minus 0 squared to the negative 1/2, which is 1/4 to the negative 1/2. Using the power of exponents, we know that because of that negative power, we can flip what's inside. So we can say this is the same as 4 to the positive 1/2 power, because the reciprocal of 1/4 is 4, or 4 over 1, and 4 to the 1/2 power is 2. So there you go. You got that y of 0 is equal to 2, right? Y of 0 is equal to 2. That was our initial condition. All right, so now let's go ahead and verify the rest of this. So we have our differential equation, y prime equals x times y cubed, and we'll plug in what we know. So we know that y prime is equal to x over 1/4 minus x squared to the 3/2. And that should be equal to x times y cubed. So y cubed is what y is equal to, right? So y is 1/4 minus x squared to the negative 1/2, and we're going to cube that. Okay, now we know when we raise a power to a power that we multiply those powers. So negative 1/2 times 3 is negative 3/2. So that right side becomes 1/4 minus x squared to the 3/2 power. I'm sorry, negative 3/2 power. Negative 1/2 times 3 is negative 3/2. On the other side, we have x over 1/4 minus x squared to the positive 3/2. And those are equal, right? Because we know that this right-hand side is the same as x over 1/4 minus x squared to the 3/2 because of that negative power. So it does check out. We can say that y equals 1/4 minus x squared to the negative 1/2 power is a solution to the initial value problem. And again, to verify that, we had to verify the initial condition. That's what we did over here. We verified the initial condition, and then we also verify that y is a solution. And so let's move on to the next and final example. So if we look at example 6, it says solve the initial value problem. Y prime equals x squared minus 4x plus 3 minus 6e to the 3x. And then it has an initial condition again, y of 0 equals 8. And so how are we going to find a solution to this differential equation? Minus 4x plus 3 equals 6, or minus 6 e to the x. Well, how do you think? How are we going to find y? Well, we're just going to, hopefully what you're thinking is we're going to find the antiderivative, right? So, I mean, we know that in order to go from y prime to y, we just take the antiderivative. So we take the antiderivative of the left side. The antiderivative of y prime is y. And we also have to take the antiderivative of the other side. So we get 1/3 x cubed minus 2x squared plus 3x minus 6e to the x, and then we have our constant of integration. And well, how do we notice when we solve? That means we want to find the particular solution, and we can because we have our initial condition, right? We know that y of 0 is equal to 8. So that means the y value is 8, and that's what we get when we plug in 0 everywhere for x. So we have 1/3 times 0 cubed minus 2 times 0 squared plus 3 times 0 minus 6e to the 0 plus c. So we get 8 equals, oops, and write 0 there. That should be 6e to the 0 power. Well, anything raised to the 0 power is 1, so that's minus 6 times 1, or minus 6 plus c. All those other terms here are 0. So this tells us that c is equal to what? C equals 14. Well, we now know our general solution, right? Since we found what the constant was, we know that our general solution is y equals 1/3 x cubed minus 2x squared plus 3x minus 6e to the x plus 14. And that's going to do it for this section. We covered all of the topics that we needed to. Go ahead and let me know if you have any questions. Have a great day. Thank you.